Welcome back. We're still in Module 10 talking about remote sensing. Last time I talked about orthometric distortion and the need to correct those distortions. So remember, if you have an image, it's just an image. If you want to be able to overlay it and measure things and use it with other data that are projected data, you'll need to do orthometric correction. So far in this module I've been talking mainly about passive remote sensing systems, and these are systems that sense the energy that's bounced off the object, usually from the sun. And there's another branch of remote sensing called active remote sensing, and those are systems that generate a signal inside of their sensor. Or inside of the hardware they're going to generate a signal, and they're going to bounce it off the object, and they're going to sense the energy that's returned from the signal that they send. So they're active, they're not passive. When you look at these three examples here, we have LiDAR, radar, and sonar. Sonar is down here, and you have to remember that this is shorter wavelengths. So in that general spectrum that I show from the sun, this would be flipped. So the gamma rays would be over here, and the radio waves would be over here. So these are all longer wavelength things. Sonar is a longer wavelength thing. Radar is out here in the microwave bands, so it's also longer wavelengths. LiDAR is in the visible and ultraviolet, so it's what we can see, and a little bit on the higher wavelength, shorter wavelength, higher energy ends of the spectrum. What does LiDAR stand for? It stands for light detection and ranging. Basically it's shining a laser down from the hardware, and that laser is bouncing off what it hits, and it's able to record the range to what it hits, depending upon the speed of light and how long it takes the signal to go out and come back. LiDAR has an additional feature that's really useful, and that is it can sense multiple returns. You can imagine something going down and hitting a tree, a piece of the canopy. It's going to bounce back. Part of that signal might make it down a little bit further and hit a piece of the canopy a little bit lower, and that could be the second return. And then part of the signal might make it all the way to the ground, and that would be the last return. So the LiDAR signal, the LiDAR hardware, the sensor is going to be able to sense multiple returns from the same source signal. It's going to allow you to get a 3D effect in your LiDAR data. What this does is it produces a bunch of points, and these are called mass points. And so these points are the intensity of the return signal and how much time it's taken for that signal to come, and their X and Y location. So there's first return, intermediate return, Z, and the last return. What you get in these are the location, X, Y, and because of the ranging, the Z for each of these points, and the intensity. So you're getting a lot of information, and it's all laser based, so it's quick, it's fast, and you have really small spatial resolution, which means you're able to detect things that are separated on the order of centimeters as opposed to feet and meters and things like that. Here's an example that shows last return LiDAR displayed in shaded relief. So remember, shaded relief is a model that attempts to give you 3D perception of what it's seeing. And you can see there are these mounds out there that appear to be there. There's vegetation, so maybe some first returns are coming back and showing you that there's vegetation. These may just be last returns where it's bouncing off the ground. You can see there may be some type of a wall or a vegetative fence here. Using the data and processing it well is going to be able to subtract the vegetation from this surface and come up with what's called a bare earth digital terrain model. And so using this LiDAR data and crunching the numbers between first, intermediate, and last returns, it's able to produce this digital terrain, which is the bare earth. And you can see when you zoom in here, in the basic last return LiDAR data, you see what look like trees here. And you can see a depression, but it's mostly trees. But some of that signal makes it through the trees and all the way to the ground, and so the processing is able to subtract the trees from that last return and come up with these depressions. And this depression here you can't even see when the tree is hiding it. So some of the data makes it through, you're able to get this depression. So it's really high resolution stuff that's going to give you a really fine picture of the terrain that it's bouncing off of. Okay, what's radar? Radar is radio detection and ranging. So LiDAR was light, radar is radio, and radio is in the microwave part of the spectrum. And it's going to do the same kind of thing. It's going to have hardware on board the plane or on board something that sends a signal out to the ground. It bounces back and it senses the intensity of that signal and how long it takes to get back. You can see again that there's going to be lots of issues with distortions and corrections, and so there's a lot of post-processing involved in making this data work. And radar, you've seen way back in World War II, I think maybe they used radar to sense incoming things. The signal bounces off things and it works really well. Sonar is what you use in the water bodies and the oceans, and that's going to do sonic waves. It's going to send out sonic waves as opposed to radio waves or light or LiDAR waves, and the sound waves are even longer wavelengths. And so those are going to go out and they're going to bounce off of objects, and the signal will be returned depending upon, again, how long it takes the signal to get out and back. The hardware is able to determine how far away this thing is, and it's able to give you an idea of how far things are. So that's the three types of active sensing, remote sensing. I should probably talk a little bit about all these different satellites that are out there. I've basically just told you about Landsat 7, which is where we get a lot of the imagery, and that's every 16 days. That's free from the government. But the government has a whole bunch of other satellites out there that have sensors on them that are specifically designed to sense certain portions of the planet or the atmosphere on the planet. And so there are things like MODIS satellites, and those satellites have sensors on them that are going to be good at determining where the water is at, what the atmospheric cloud situation is like, where the snow is, things like that. So each one of these satellites is going to have a custom designed sensor set in it that allows you to get information about the planet and the atmosphere. You can go out to the Earth observing system and you can learn about these, and a lot of the times you can download the data that's been post-processed properly, and you can use that data to help you learn about the Earth. Okay, so that was active sensing, LiDAR, radar, sonar. That's the end of the remote sensing coverage. Remember, again, remote sensing is a really deep topic. You can spend a whole career doing remote sensing. I just covered the surface of it. If you want to learn more, you should take one of the other courses in the geography department that involve remote sensing. Next time, I'm going to talk about GPS concepts. So that's going to be the last kind of major concept we're going to cover in this lecture series, and I'll see you next time.